This is the first lecture of 2 lectures that we're going to have on selecting the best regression equation. Today, we're going to take a look at steps that we can take to find the best regression equation. We'll define the maximum model. We'll take a look at some selection criteria, and then we will explore the forward selection and backward elimination methods of selecting the best regression equation. So consider this situation. We want to model the price of a house using its living area, the age, the number of bedrooms, the number of bathrooms, and the number of fireplaces. The question here is, why would including all of these predictors not necessarily be the best choice? Well, the reality of the situation is that not all of these predictors may ultimately be significant in predicting price. We don't necessarily need to include predictors that have low correlations with the price of a house. So the next question that we have to consider is, how can we decide what the best model is? And I put best model in quotes because there's not really one definition for the best model. There are a lot of different ways that we can arrive upon the best model, so best model is very subjective. Now, one way of going about this is to use a model selection criterion as well as model selection techniques in order to determine the best set of predictor variables. Now, selecting the best regression equation is really a 5-step process that we're going to spend the entirety of the next 2 lectures talking about. Step 1 is to specify the maximum model. Step 2 is to specify the criterion that you're going to use in order to select that model. Step 3 is identifying the strategy you're going to use in order to select the variables that end up in your final model. Step 4 is actually conducting the specified analysis. And step 5 is evaluating the reliability of the final model that you end up choosing. Now, the maximum model is defined to be the largest model, or the model with the most predictors, variables, that we consider at any point throughout the model selection process. The size of the maximum model is denoted by K, and it's largely dependent upon the sample size. One requirement that has to be true is that the total number of degrees of freedom in the error term, or n minus k minus 1, has to be greater than 0. In other words, the number of predictors in your model cannot possibly exceed the total number of observations that you have in your data set. One weak recommendation that your textbook offers is that the degrees of freedom in the error term should be at least 10, but the rule of thumb that most statisticians go by is that the total number of observations should be at least 5 times the number of predictors that you have in your model. Another way of thinking about that is that you can use up 1 degree of freedom in the regression for every 5 observations that you have in your data set. The other thing to keep in mind is that you can't include predictors that don't have any variability in their values. So for example, it's impossible to include gender in a sample that consists of all females, because every single observation for that variable would be coded as either 1 or 0. You wouldn't have any males in there. It's also impossible to include an interaction between, say, gender and race if you don't have any black females. Now, choosing your maximum model is largely dependent upon what you're trying to accomplish. There are benefits of using a large maximum model, but there are also benefits to using a smaller maximum model. One benefit to using a large maximum model is the ability to consider more complex predictors beyond the main effects. If you have a large maximum model and a large amount of data that you're working with, you can put in higher order powers, an x squared, an x cubed term. You're allowed to transform the main effects a little bit easier. You can put in interactions between many different pairs of your variables to see if those interactions are significant. And you can also put in a lot more control variables. A larger maximum model also helps to reduce the chance that we make a type 2 error. In this case, a type 2 error would be leaving out a significant predictor that has a non-zero regression coefficient. We want to make sure that if a predictor has a high correlation with the response, and it's actually going to be beneficial in our final model, that it has a chance to be in that final model, which we can't accomplish if we have a smaller maximum model. Now, on the other hand, there are some benefits of using a small maximum model. One benefit is that it tends to be a little bit more reliable if the goal is to predict future observations. If you have a smaller set of variables to choose from, you're going to end up with a smaller final model in all likelihood, and you won't risk overfitting the data, which is an issue that we'll talk about a little bit later on. A small maximum model also reduces the chance that you make a type 1 error. In this case, a type 1 error would be including a predictor that actually has a regression coefficient equal to 0. So we include a non-significant predictor in our final model whenever, in fact, the model selection process found that that predictor should be in the model. So that is one benefit of using a small maximum model, is it reduces the chance that we put in predictors that aren't significant into the final model. So looking back at our house price data, we have 5 different predictors that we are choosing from. So let's set up our maximum model to be the model that has all 5 of our main effects with no interaction terms and no higher order terms. So we'll let x1 be living area, we'll let x2 be age, we'll let x3 be the number of bedrooms, x4 is the number of bathrooms, and x5 is the number of fireplaces. Now, one rule of thumb that we also tend to go by is if we're trying to figure out if an interaction term should be in the maximum model, we have to think about if it makes sense to even really consider whether an interaction exists between any of these predictors. And based on looking at these 5, I don't really think there's any reason to believe that an interaction exists between any of these predictors, so it might make sense just to work with these 5 main effects. Step 2 in the model selection process is deciding upon your selection criterion. The selection criterion is a metric that we're able to compute for every single potential final model, and we compare these values against all other models that are in contention in order to determine what the best one actually is. Now, given your full and reduced models, there are several different selection criteria. One way that we can go about this would be to run partial f-tests or multiple partial f-tests. So the f statistic comparing the full and the reduced models would be one selection criterion. A second one would be the r-squared, and we've already looked at how we can use r-squared in order to decide upon what the best model is. 2 other new metrics that are a little bit more useful, though, are the adjusted r-squared and Mallos Cp Criterion. Now, thinking back several weeks, r-squared is defined to be the proportion of variability in the response that is explained collectively by all of your predictors in the model. And r-squared was calculated by taking the difference between the total sums of squares in the entire regression, SSY, subtracting off the sums of squares due to the error, the SSE, and then dividing by SSY. Now, if you recall, adding another predictor into your model can never decrease the value of your r-squared, because every time a predictor is added into the model, it helps to explain some minute amount of variability in the absolute worst case scenario. So what happens is that additional predictor that we add in siphons some of the sums of squares due to the error out and puts it into the explained variability, the sums of squares due to the regression. And in the absolute worst case scenario, adding a predictor is going to do nothing to change the r-squared. It leaves the SSR and the SSE alone. However, one issue that we ran into whenever we just looked at r-squared was the fact that if you put in a predictor that's not significant, you're guaranteed to see that r-squared value increase at least by a little bit. And so you have to consider whether or not putting that predictor in is actually worthwhile. This is where r-squared becomes a little bit more difficult to use. So instead, what we can use is the adjusted r-squared. The adjusted r-squared is calculated in a similar way that we calculate out the regular r-squared. What it does is it still explains how much variability in the response is being explained collectively by the predictors, but adjusted r-squared actually imposes a penalty for adding additional terms that are not significant. Adjusted r-squared is calculated by taking 1 minus the SSE divided by n minus k minus 1, and then dividing that by the total sums of squares SSY, divided by n minus 1. What makes adjusted r squared different from the regular r squared is the fact that your adjusted r squared is able to decrease if a predictor is inserted into the model that is not useful. So by dividing by n minus k minus 1, degrees of freedom in your error term, it basically penalizes your model if you include an insignificant predictor. This allows for easier comparison whenever your models have different numbers of predictors. So what you might see before with just regular r squared is if you have a model with 3 predictors, you could have an r squared value of, for example, 0.7. Then whenever you put in an additional predictor, it may not be significant, but you would still see an increase to your r squared up to maybe 0.71 or 0.72. Adjusted r squared fixes that issue. What adjusted r squared is going to do is it's going to say, okay, for this model that has 3 predictors, we have an r squared of 0.7. If we go ahead and put in another predictor, and that predictor happens to not be significant, adjusted r squared isn't tricked like the regular r squared is. Adjusted r squared is going to penalize you for putting in a predictor that is not significant. So whenever you look at the adjusted r squared for the model that has that 4th predictor, you will actually see a reduction in the value to maybe 0.68 or so in order to penalize you for the fact that you've put in a predictor that is not significant and it's not really helping you understand the response. So let's take a look at an example. What we want to do is predict sales in millions of dollars at 41 retail stores using 5 different predictors. We have advertising costs, which is x1, the size of the store, which is x2, employee retention percentage, x3, customer satisfaction percentage, which is x4, and then a dummy variable indicating whether or not a promotion happens to be going on at the time, and we'll denote that by z1. We want to calculate out the adjusted r squared for the model that includes only advertising costs and whether or not a promotion is going on. So the output that you see over on the bottom right is the output that includes only these 2 predictors. We have an SSR of 8.133, an SSE of 4.696, and a total sums of squares of 12.829. So our adjusted r squared is going to be 1 minus the SSE 4.696 divided by the number of degrees of freedom in the error term, 41 observations altogether, minus the 2 predictors in the model, minus an additional 1, giving us 38. Then we divide that by the total sums of squares, 12.829 divided by n minus 1, 41 minus 1. That's going to give us 1 minus 0.1236 over 0.3207, which gives us an adjusted r squared of 0.6146 for the model that includes only advertising costs and whether or not a promotion is going on. But let's see what happens if we put in employee retention percentage into the model along with advertising costs and the promotion dummy variable. Take a look at the output in the bottom right. Notice that we have our adjusted sums of squares, or our type 3 sums of squares, meaning this is the contribution to the model if this predictor is added in last. For employee retention percentage, the adjusted sums of squares is 0.008. So it's contributing a very, very small amount to the explained variation, given that advertising costs and the promotion dummy variable are already in the model. This is going to be reflected whenever we calculate out the adjusted r squared. Our adjusted r squared is going to be 1 minus the SSE, 4.688, divided by the degrees of freedom in the error term, which is now 37, because we have 3 predictors in the model. So notice that the SSE didn't change by much, but now our denominator is 37 instead of 38. The denominator in the entire calculation stays the same. It's still 12.829 divided by 40. So now what ends up happening here is that the numerator is very different from what we had before, 0.1267. We divide that by 0.3207, subtract that from 1, and we actually end up with an adjusted R-squared of 0.6049, which is smaller than the adjusted R-squared that we had in the previous model that only had 2 predictors in it. And so like we just saw, whenever we added employee retention percentage into the model, the adjusted R-squared decreased. The reason this happened is a result of the relationship that employee retention percentage has with the response. In the bottom right, we have the correlations between each of the individual predictors and the response, which is sales. And in this case, employee retention percentage is not highly correlated with the sales at the store. So what we did was we put an insignificant predictor into the model that's taking up a degree of freedom. And ultimately, it wasn't worth it to include this predictor in the model and also simultaneously use up that degree of freedom. Because adding this predictor into the model only very slightly reduces the sums of squares due to the error. It doesn't contribute very much to the explained variability. It's not really helping us understand sales all that much better. So we basically put a useless predictor into this model. One other metric that we can use in order to decide upon a final model is called Mallos Cp Criterion. Now, Mallos Cp Criterion basically takes your maximum model and it compares it against all of your different candidates for what the final model could be. We're going to consider these our reduced models. Now, in order to calculate out Mallos Cp, we take the sums of squares due to the error for the reduced model, divide by the MSE for the full or maximum model, and then from that we subtract off the quantity n, which is the number of observations in the data, minus twice the number of predictors in your reduced model plus 1. Now, Mallos Cp is compared against p plus 1. If Cp is greater than p plus 1, if Mallos Cp is greater than the number of predictors in your reduced model plus 1, then that model tends to exhibit lack of fit, and it often has high prediction error, and it could also be overfit. So you are fitting your model very close to the data that you have in your current data set, but if you went to make predictions later on new data that your model has never seen before, then that model would very likely do a poor job at predicting those new observations. On the opposite end of the spectrum, models where Mallos Cp is considerably less than p plus 1 are going to have high bias or tend to be underfit. You actually don't have enough information or predictors in your model. In order to select the best model or the final model, we're going to choose the model where Mallos Cp is as close to p plus 1 as possible without going over. We still want to make sure that Mallos Cp is less than or equal to p plus 1. So it's basically like playing The Price is Right. You want to get as close to p plus 1 as you can without going over. One other note here is that Mallos Cp for the full model, for your maximum model, is always going to be equal to p plus 1. And so it's always going to be a model that is under consideration for what the final model should be. So let's go back to our house price data. Again, we want to model the price of a house using 5 predictors: living area, age, number of bedrooms, number of bathrooms, and number of fireplaces. Over on the left, we have the output for the maximum model that has all 5 predictors. What we ultimately want to calculate is Mallos Cp for the model that includes only living area and number of bathrooms. The output that you see over on the right is the output that includes only these 2 predictors. So to calculate Mallos Cp, we're going to take the SSE for the reduced model that has only living area and bathrooms, 628,632, and divide by the MSE for the full model, 4,226. Now, the data for this situation is posted up on CourseWeb. It turns out there are 150 observations in the data set, so we'll take 150 and subtract off twice the number of predictors in the reduced model plus 1. 150 minus 2 times 3. That's going to give us 148.75 minus 144, meaning that Mallos Cp for this model that includes only living area and number of bathrooms is equal to 4.75. If, on the other hand, we want to include two additional predictors, we want to include number of bedrooms and number of fireplaces as well, we're going to keep the same maximum model. So the output on the left is still the same, but we're going to have to run a new reduced model. We're going to run the model that has all four of these predictors of interest. In this case, we're going to have a new sums of squares due to the error for the reduced model, 609,304. But the MSE for the full model is going to stay the same, 4,226. The second piece of Mallos Cp Criterion is going to be unchanged except for the number of predictors. We're going to be subtracting off 150 minus 2 times 4 plus 1 now, or 150 minus 10, because we now have 4 predictors in the reduced model instead of just 2. This is going to give us 144.18 minus 140, meaning that Mallos Cp for the model that includes these 4 predictors is equal to 4.18. Now at this point, we've calculated Mallos Cp for 2 different models, and that actually allows us to make a direct comparison. We can decide which of the 2 models appears to be a better choice. Now looking at model 1, which had only x1 and x4, we had Mallos Cp equal to 4.75. That model only had 2 predictors, so whenever we compare Mallos Cp of 4.75 against the number of predictors plus 1, Mallos Cp is greater than the number of predictors plus 1. So this model that includes only x1 and x4 probably has high prediction error from missing important predictors. We probably don't have all of the necessary highly significant predictors in this model. On the other hand, model 2, which includes x1, x3, x4, and x5, had a Mallos Cp value of 4.18, and this actually ends up being less than the number of predictors plus 1. 4.18 is less than 5. This model could be slightly underfit because it is pretty far below the number of predictors plus 1. However, model 2 is going to be the better option here because Mallos Cp is less than p plus 1. We only want to consider models where Mallos Cp is less than p plus 1. Models where Mallos Cp is greater than p plus 1 are going to tend to be overfit, and again are going to have high prediction error and don't necessarily end up being the best final models to choose. Step 3 in your model selection process is specifying the strategy that you want to use in order to determine what your final model is. Now, there are a lot of different methods for determining how many predictors and which variables get included in your final model, and we're going to take a look at all of the following. We have forward selection as one option. We have backward elimination as a second. There is stepwise selection. There's chunkwise selection. And there is all subsets regression, also known as all possible regressions. Now, any of these model selection strategies that you see listed here can be paired with any of the selection criteria. The thing you have to keep in mind, though, is that one combination of model strategy and selection criteria is not necessarily guaranteed to give you the exact same set of predictors in your final model as some other combination. So let's first take a look at the forward selection algorithm. Step 1 in the forward selection algorithm is to choose a level of significance, alpha, in order to insert variables into your model. Step 2 is to take a look at the correlation matrix between your response and each of your predictors. The predictor that has the highest correlation with your response should be the first predictor that you insert into the model. And this is where we're going to start taking a look at building our final model. What we can do next in the forward selection algorithm is calculate out the partial F statistic for every single variable, acting as if it's going to be the next one to enter the model after the one that we put in step 2. And we're going to calculate out the corresponding p-value for every single one of those contenders. Step 4 is to identify the variable that has the lowest p-value if it's going to enter the model next. We'll call that p-min. And step 5 is going to be to compare the p-value from step 4 with the level of significance that we choose. If the p-value for that predictor is less than alpha, then we're going to insert this predictor into the model, and then go back and repeat steps 2, 3, and 4. However, if this minimum p-value is greater than alpha, then what that means is that the final model is going to consist of all of your predictors that are currently in the model. What this is saying is that the predictor that would enter the model next, because it has the smallest p-value out of the predictors that are not currently in the model, that p-value is too large in order to make it a useful predictor. That predictor is not significant, so at this point we want to stop, cut off the forward selection algorithm, and decide upon our final model being the one where we stopped here in step 5. So going back to our house price example, where we're modeling the price of a house based on these 5 different predictors, we have the correlation matrix here. What we're interested in is the first column of this correlation matrix, because these are giving us the correlations between each predictor and our response house price. We want to perform the forward selection algorithm in order to choose the best model using 0.1 as our level of significance for a predictor to enter the model. Now, taking a look at the correlation matrix, what we see is that living area should be entered into the model first. It has the highest correlation with price at 0.811, and so this appears to be the best predictor that we can start out with building our model. Now, step 2 in the model selection process is to add in each of the other 4 predictors into the model with living area to see what the p-value is for each of these other 4 predictors, given that living area is already in the model. So the output in the top left puts age into the model as our next contender after living area. The output in the top right puts number of bedrooms into the model after living area. Bottom left has number of bathrooms after living area, and the model on the bottom right has fireplaces added in immediately after living area. What we then want to do is take a look at the F statistic and do a partial F test for the addition of each of these individual predictors, given that living area is already in the model. Now, what we see here is that the number of bathrooms should be entered into the model next. Out of the 4 contenders, the number of bathrooms has the smallest p-value. It's less than 0.001. Looking at age, that had a p-value of 0.062, so although it's less than 0.1 and would have been a contender for being added in, its p-value was not less than the p-value for the number of bathrooms. Number of bedrooms and number of fireplaces both had p-values up above 0.1, so they wouldn't have even been contenders anyway. So because the number of bathrooms has the smallest p-value out of the 4 remaining predictors, given that living area is already in the model, number of bathrooms is going to be entered into the model next. Then what we do is we keep living area and number of bathrooms in the model, and we put in each of the other 3 predictors and continue to do additional partial F tests. Putting age into the model after both living area and number of bathrooms are in the model gives us an F statistic of 0.01. Putting in number of bedrooms after both living area and number of bathrooms gives us an F statistic of 0.27. And putting the number of fireplaces into the model after living area and number of bathrooms gives us an F statistic of 4.08. This is going to be the variable that we're going to consider for inclusion in the model. Looking at its p-value, we see that the p-value is less than 0.1, it's 0.045. So we're going to insert the number of fireplaces into the model because, again, it has the smallest p-value for the 3 remaining predictors, given that living area and bathrooms are already in the model, and that p-value is also less than 0.1. We now have 3 predictors in our model: living area, bathrooms, and fireplaces. So now what we're going to do is test age and test the number of bedrooms, given that these other 3 predictors are already in the model. Now notice that if we include age in the model with the other 3 predictors, we get an F statistic of 0.04, which gives us a p-value of 0.845. If we do the same thing for number of bedrooms, our F statistic is 0.53 for a p-value of 0.467. So at this point, no additional variables should be inserted into this model. Both of the p-values for age and number of bedrooms are greater than the 10% level of significance that we specified back at the very beginning. So we should stop, and our final model is going to be the model that includes x1, living area, number of bathrooms, which is x4, and number of fireplaces, which is x5. Now, the backward elimination algorithm actually works in a very similar way to the forward selection algorithm, only, as you might guess, it works in reverse. What we do is, in step 1, we choose a level of significance, alpha, in order to remove variables. We then determine the regression equation for the maximum model. We fit the maximum model on our data. And we calculate the partial F statistic for every predictor as if it were the last one to enter the model, and calculate the corresponding p-value. We then want to identify the variable in the model that has the highest p-value. We'll call that p-max. And we'll then compare the p-value from step 4 with our level of significance. If the maximum p-value is greater than alpha, then we're going to remove this predictor from the model and then go back and repeat steps 2 through 4. However, if the maximum p-value out of the predictors that are still in the model is less than alpha, then we're done. The final model is going to consist of all variables that remain in the model because everything that is currently in the model is significant. So let's go back to our house price data and use backward elimination with a 10% level of significance for removal from the model to determine our final model. The output that you see has fit the maximum model. We have all 5 of our predictors in that model. Notice we also have our adjusted sums of squares. So we have our type 3 sums of squares. This is again making the assumption that each of these predictors is entering the model last after the other 4. Notice that we have 2 predictors here, age and number of bedrooms, where the p-value is greater than 0.1. Because age has the higher of the 2 p-values, 0.679 compared to 0.417, we're going to remove age from the model because, again, it's the largest p-value that is above 0.1, our level of significance. Then we're going to rerun the model with living area, bedrooms, bathrooms, and number of fireplaces in the model. We're going to take age out, and we're going to consider this model that only has 4 predictors in it. We're again going to do the exact same thing. Take a look at the p-value for each of the predictors, assuming it's entering the model last. In this case, the number of bedrooms is the only predictor that has a p-value greater than 0.1. So as a result, we're going to remove the number of bedrooms from the model because it is not only the largest p-value that's above 0.1, it's the only p-value that's above 0.1. In step 3, we're now going to fit the model on only living area, number of bathrooms, and number of fireplaces. Again, looking at the p-values, we notice this time that all 3 of these p-values are less than 0.1. That's an indication that all 3 of our predictors are significant. So at this point, we shouldn't remove any additional predictors from the model. The largest p-value for number of fireplaces is below 0.1, which is an indication that all 3 of these predictors are significant. As a result, our final model is going to be the one that includes x1, living area, x4, number of bathrooms, and x5, number of fireplaces. So to finish things off, let's recall that both forward selection and backward elimination gave us the same final model. They both found the living area, number of bathrooms, and number of fireplaces should be included in the final model. So the question here is, Well, if we're using the same level of significance, will forward selection and backward elimination always yield the same final model? And the answer here is actually no. So consider this potential situation. Let's say we have three predictors, x1, x2, and x3. Let's also say that these predictors are highly correlated with one another. Now, forward selection may choose x1 if it's going to be the most correlated with the response. So you'll start out with x1 as a definitive predictor in your final model. However, if these predictors are highly correlated with one another, what could happen is that backward elimination could see that the model does really well with the combination of x2 and x3, so it decides to leave those two predictors in the model, and it could ultimately end up removing x1 from the model first if it deems that the best model is the one that includes x2 and x3. So while a lot of the time forward selection and backward elimination will give you the same final model, it's not always going to be a guarantee.